All right, let's get right into it. Today, we're diving deep into the secret lives of atoms, trying to understand what you might call their destiny. We're going to figure out why some atoms seem born to give electrons away, while others are destined to snatch them up.
You know, it all starts with something you've probably seen a million times. See those chalky white stains that build up on your shower head? Or that crusty scale that can clog up a water heater? Well, that's what people call hard water.
And the culprits behind all that mineral gunk? They're totally invisible, hiding right there in your water. They're charged atoms called ions, things like calcium and iron. But wait a second, how did they get charged in the first place?
So how does a perfectly neutral atom end up becoming a charged ion? Well, it basically comes to a fork in the road. It has one of two fates. It can go positive or it can go negative.
Let's break this down. On one side, you have the givers. These are atoms that lose one or more of their negatively charged electrons. And since they've lost some negative charge, they end up with an overall positive charge. We call these cations. On the other side, you have the takers. These atoms grab extra electrons, which tips their scales negative, and we call those anions.
Just to really lock that in, cations are the ones that lose an electron, leaving them with a positive charge. And here's a little trick I've always used. Think of a cat. Cats have paws, they're positive. Yeah, that's how I remember it. Cations are positive.
And you guessed it, anions are the complete opposite. They take on an extra electron, and that gives them a net negative charge. It's really as simple as that. Givers and takers.
But why? Why are some atoms givers and others takers? It's definitely not random. It's actually all decided by this intense inner tug of war going on inside the atom, governed by a couple of key forces.
So, the first force we need to talk about is something called ionization energy. The easiest way to think about this is as the price or the cost an atom has to pay to get rid of an electron. It's the energy you literally have to put in to rip that electron away from it.
And what's so cool is how predictable this cost is. If you just look at the periodic table, the price goes way up as you move from left to right and as you go up from the bottom. Why? Well, smaller atoms hold onto their electrons a lot tighter. The absolute most expensive atom to ionize, that's helium, way up in the top right. And the cheapest, that would be francium, all the way down in the bottom left.
Okay, so if ionization energy is the cost to lose an electron affinity is the reward an atom gets for gaining one. It's the energy that's actually released when an atom successfully snags a new electron.
And the trend here is pretty similar. That reward, that energy payout gets bigger as you move to the right on the table. But there is a huge exception, the noble gases, that column on the far right. For them, the reward is basically zero. They have no interest in another electron. And why is that? It's because their outer electron shells are already completely full. There's literally no room at the end.
So we've got a cost to lose an electron and a reward for gaining one. But what's the end game? What's driving this whole process? Well, it all boils down to one single, powerful motivation: the search for stability. This is a fundamental law of the universe, really. Nature just prefers to be in a lower energy state. Think about a ball at the top of a hill. It will roll down all by itself to get to a lower, more stable position. Atoms do the exact same thing. They will spontaneously change if it means they can get to a lower energy, more stable state. And in the world of atoms, when it comes to stability, there is one magic number that rules them all, and that number is 8.
This brings us to the big idea, the octet rule. It's pretty straightforward. It just says that atoms will do pretty much anything, gain, lose, or even share electrons to end up with a full outer shell of 8 electrons. That full set, that octet, is an incredibly stable, low-energy arrangement. It's exactly what the super-stable noble gases have and what all the other atoms want.
Let's make this real with a classic example: sodium. A regular sodium atom has just one single lonely electron in its outermost shell. And since it's a metal on the left side of the table, the cost to lose that electron, its ionization energy, is super low. So it gladly gives it away. And as soon as it does, the shell underneath becomes its new outer shell, and guess what? That one is perfectly full with 8 electrons. Boom! It's now a stable sodium ion with a +1 charge.
So, we have these atoms that want to be givers and atoms that want to be takers. So what happens when they finally meet? This is the moment where their destiny is fulfilled.
Okay, let's just recap our cast of characters here. The metals, on the left of the table, they are natural-born givers. It's cheap for them to lose electrons, and they get no reward for gaining them.
The nonmetals, over on the right, they are the takers. It costs a lot to take their electrons, but they get a huge energy reward for grabbing a new one. And the noble gases. They're already stable. They're happy to just watch from the sidelines.
So when a giver, like a metal atom, just happens to bump into a taker, like a nonmetal atom, the outcome is basically written in stone. That electron transfer is inevitable. The normal everyday energy of atoms bouncing around is more than enough for that electron to make the leap. And this right here shows you why it's a done deal. Look at the energy math. It takes just a tiny bit of energy for the electron to leave the metal, but the energy released when the nonmetal grabs it is much, much bigger. The net result? It's a huge win for the whole system. Everything moves to a lower, more stable energy state.
And just like that, the transfer is complete. The metal has become a stable, positive cation. The nonmetal has become a stable, negative anion. They both achieved their full octet. They have fulfilled their ionic destiny.
Which brings us to one last really interesting question. We've just created a positive ion and a negative ion, and they're sitting right next to each other. So, what happens when opposite charges attract? Well, my friends, that is where a whole new adventure begins.